Thank you very much. Thank you for coming after lunch. So we are at the quantum machine learning session. I will try to give you some examples of what quantum machine learning can do. And please stick around after the session. There will be some discussions as well if you want to learn more about quantum machine learning and where we are. All right, so I will mostly be focusing on one canonical problem of machine learning, which will be classification. And I will be trying to say more about both the supervised and the unsupervised case. So a very quick overview of quantum algorithms. I think the main reason that we are all here today is because Peter Shor in 1993, he came up with this amazing polynomial time quantum algorithm for factoring big numbers. And this was kind of the result that kind of jump-started the whole area of quantum computing and quantum algorithms. And after that, there have been quite a few algorithms that had to do with number theory and more related to cryptography. It took a few more years after Shor's algorithm in the late 90s, where Love Grover came up with another very powerful quantum algorithm that had to do with searching. The idea is that if you have a quantum computer, if you have a number of elements and you're trying to find which element is marked, then you can actually do that in a time which is quadratically faster than any classical algorithm would do this task. And this also gave rise to a number of different algorithms, including different techniques like quantum walks that we heard about before. And this type of algorithms, while factoring is supposed to give an exponential speedup compared to classical algorithms, these algorithms that are based on Grover search can give you a quadratic speedup, but they're very versatile. They can be used for many different applications. The main algorithm I want to talk about is the HHL algorithm, which was actually found by Haro, Hasidim, and Lloyd in 2009. And it's a little more difficult to explain than factoring or search. The main idea is that quantum computers can provide a quantum solution to a system of linear equations, and the running time is, in certain cases, exponentially faster than the classical algorithm will take in order to solve the same system of linear equations. So there are a couple of things that we have to be very careful about, and this is why quantum machine learning is also a field which has many subtleties. So here we say that the quantum computer provides a quantum solution, meaning that at the end of this process, you don't get the classical description of the solution to your linear system. What you get is a quantum state that corresponds to this solution. Sometimes this is useful, sometimes it's not so useful, okay? And the other case is that the other property of the algorithm is that its running time depends, on one hand, very favorably with respect to the dimension of the system. So while the classical algorithms depend polynomially on the dimension of the system, meaning the number of equations and the number of variables that you have, the quantum algorithm depends only logarithmically on these parameters, which is very good. On the other hand, the algorithm also depends on other parameters that have to do with the specifics of the problem that you're trying to solve. For example, whether your matrix is well-conditioned, whether your matrix is sparse, if it's low rank, and all these kind of questions. So the reason I'm saying all this is because the HHL algorithm is a very powerful quantum algorithm, but one has to be very careful what kind of claims one makes when using this type of algorithms. Okay? It's not something that by default and off the shelf will actually provide you an exponential speedup. And the whole point is to actually find the cases in the real-world applications where you could use this algorithm and show that you can have a speedup in practice. Okay? Okay, and after this algorithm, there was somehow a large number of applications, both in convex optimization and in machine learning. Many of these results came also by Seth Lloyd and other collaborators. We had support vector machines. We had principal component analysis, classification. There are also a second type of algorithms that have to do with convex optimization that use the same type of linear algebra techniques that the HHL algorithm uses. For example, for linear programming, semi-definite programming, gradient descent, interior point methods. So all this type of algorithms, all this type of methods that are quite widely used for classical optimization, one can provide quantum algorithms that sometimes could actually be much faster. Not always, as is always the case. So before I go on, I just want to put 3 remarks on quantum machine learning. So the first one is that I really think that if we want to harness the full power of quantum machine learning, then we will need, at some point, full-scale computers with quantum access to classical data. I'm not saying that there's nothing else we can do with NISQ-era machines or with computers, small-scale computers that don't have quantum access to the classical data. But if we really want to access the full power of quantum machine learning algorithms, then most probably we will need to have this type of full-scale computers. The second thing that actually it was supposed to be somewhat unexpected, but Adam on the first day already quoted me on that. So quantum machine learning is at the same time, I find it very overhyped and underestimated. So how is this possible? Well, there are other people who overhype it and other people who underestimate it, so it is possible. It's overhyped because it's very tempting to look at these algorithms and try to see, and without really looking into the details, say that, OK, I can get an exponential speedup for almost all the problems I would care about in machine learning, in optimization. And there has been a lot of hype over this. On the other hand, machine learning is not the cleanest science in some sense. For theoretical computer scientists, there are always these caveats, there are always these subtleties. When is it faster? When is it not? This is not worst-case analysis. I don't know whether it's going to work in practice or not. So there are also people who to some extent, underestimate the power of quantum machine learning. And I think the truth is somewhere in between. And what we're trying to do here is try to actually figure out what are really the problems where we can have such speedups for real-world applications. But to me, quantum machine learning is also one of the most convincing reasons that we have to actually build quantum computers, full-scale quantum computers. So I used to say this is the most convincing, but then Scott said that the most convincing reason is to silence the QC skeptics. So I just put one of the most convincing reasons to build real quantum computers is because they could potentially have these wide applications in optimization and in machine learning. All right, so let me start with one example of quantum machine learning application. Scott also talked about this in his talk. So we're talking about recommendation systems. What is the problem? You go to Amazon. You are one of the 600 million users of Amazon. You have already bought some products. You have bought some books. And then Amazon wants to recommend some product that it will be good for the user, and you will be happy, and you will spend even more money on Amazon. Okay, so this is the main question. Of course, we can translate this question into a mathematical problem. And this is somehow, it's a problem that has to do with linear algebra in the sense that what we really have is this matrix of users and products, and the elements of this matrix kind of define the preference of this product for this user, or the value of this product for this user. And what we know is very few elements of this matrix. We know, for example, that user A bought book B and he was happy. Okay? But most of this matrix is not known. And the goal of a recommendation system is to actually try to fill up this matrix and find products that would have a good value for each user that comes into the system. Okay? One can go one step further and can see that basically if you want to solve this problem, then one way of doing it would have to use something which is called singular value estimation. Again, we're going a little bit more into linear algebra. If we knew somehow the singular values and the singular vectors of this matrix, then we could provide a good solution to this problem. But these are problems which are kind of hard classically, meaning that they depend on the dimension of the matrix. And if we're talking about Amazon, we're talking about 100 million users and 600 million products. These are not matrices which are easy to manipulate somehow, right? So what we did a couple of years ago is that we provided a quantum procedure to actually solve somehow this problem exponentially faster in some sense. There were quite a few improvements afterwards on this algorithm that made the algorithm even more robust on the errors than our algorithm had. But what we could say at that point is that quantum computers could provide recommendations, and here is where I used to say exponentially faster, so now I have to change it and just say fast or faster, okay? So why do I have to say that? Because this is not the end of the story. As Scott said, that after this algorithm was published, people tried to understand whether such type of algorithms are possible or not possible classically, okay? And here is basically what happened. We have this quantum algorithm, and we know how to analyze its running time. And its running time depends on three main quantities. It's the number of users, the number of products, and the number of types of users. So as we said, Amazon might have 600 million users, but we are not 600 million unique users, in the sense that many users are very similar to each other. And this is why recommendation systems can actually work, because I can use data apart from a number of users to say something about a different user, because there is a similarity between these users, okay? So the number of types of users is actually much smaller than 600 million. Here I put 100. It could be 1,000. This will only make my point clearer, but at least we cannot expect the type of users to be 3 or 5. Let's say they're 100, okay? So the running time of the quantum algorithm was, something that would give you a 10 to the 3 running time. Well, let's say 10 to the 3. Then the best previous classical algorithm would give you something that actually depends on the number of products and not on the logarithm of the number of products. This is why it was much worse, and this is where we were getting this exponential speed up. So the running time of this kind of classical algorithm was expected to be something 10 to the 12, okay? And then there was this new classical algorithm, or quantum-inspired, which is kind of the word of the day, quantum-inspired classical algorithm that has the same dependence as the quantum one when it comes to the users and the products, but has a very bad dependence on the types, on the number of types of the users. And this actually gives you a running time that scales to something like 10 to the 33. So what happened here, we had an exponential speed up. That was a speed up between 10 to the 3 and 10 to the 12 for the instances or the size, the instance sizes that we cared about. And we lost this exponential speed up. We ended up with only a polynomial speed up. And the polynomial speed up went from 10 to the 3 versus 10 to the 12 to 10 to the 3 versus 10 to the 33. So I still think that quantum machine learning is not dead. We actually, have an even bigger advantage than we had before in this type of algorithms. Of course, one could try to improve the classical algorithms, and I think this is a very interesting question, and we should try to address this issue. All right, so let me go on to the second main example, which is classification. So first I will talk about supervised learning. So what is supervised learning? I give you some images, let's say, with some labels. So I tell you that I have these digits, and I tell you that the first image is a 3, the second is a 4, the other is a 2, and so forth. So what you need to do is come up with an algorithm that kind of is trained on these labeled inputs, so that when a new image of a digit comes into the system, then the algorithm by itself can say, OK, this is a 3 or this is a 5. OK? So this is kind of the supervised learning scenario. And we tried to find out whether a quantum algorithm for this classification problem can actually run faster than classical algorithms and also give good results, good accuracy. OK? So the first thing we had to do is come up with a way to classify. And one of the main ways that people classify is that you take these images, you imagine these images are points in some high-dimensional space, and then you kind of look at the distances between points, and you cluster points which are close to each other together, and you label these points according to the labels that you have. Okay? So we did this in a quantum way, and I want to say that one of the main things that we use that had been used before many times is that quantum computers have the ability to estimate distances between quantum states in a way which is very efficient. So if you know how to create these quantum states that correspond to these vectors that correspond to your images, for example, then it's very easy for a quantum computer to actually estimate the distance between these these points, meaning that the time to estimate this does not depend on the dimension of these vectors. Okay? Of course, we have to assume here that one knows how to create these quantum states, and if creating these quantum states is very difficult, then your quantum algorithm also has a big overhead. So I want to say two things for this classification. Basically, what we showed is that the classification is no harder than actually creating these quantum states. So if your data comes from some quantum processes, so then you have for free that you have these quantum states, then it's no more difficult to create the states than to actually classify them. Okay? And the second thing is that the accuracy that we got is comparable to some classical Sedroid classifiers. What we got for the MNIST data set, which is this data set that I'm talking about, was roughly 67%, which is not great, right? So classical algorithms can get up to 98 or 99%. What we got with this classification is 67%. This is not very good, so we had to work harder. So then we had to come up with a new technique, which is called dimensionality reduction. Well, actually, the technique is a classical technique that people in machine learning use all the time. So we used a specific dimensionality reduction technique that is called slow feature analysis. And slow feature analysis came up in neurosciences when people were trying to understand the following. When the eye sees, if I move a little bit, then my image changes completely. But somehow my brain is able to understand that what I'm seeing is just people in the audience sitting and looking at or listening to me, or I hope so. So how can the brain process this series of images that is changing a lot, but somehow come up with some feature, which is the fact that you are an audience sitting here, and how can it grasp this feature that changes very slowly or not at all during this series of images? Okay? So we used this technique. We encoded our images in quantum states, and here we used the second very important quantum tool that we have, which is quantum linear algebra. This is the same type of tools that HHL algorithm uses for solving linear systems, because solving linear systems is just inverting a matrix. So here we didn't have to invert a matrix, but we had to multiply a matrix with a vector. All these type of algorithms have a common thread under them, which is that quantum computers, in many cases, can do linear algebraic operations in sometimes faster than classical computers. Okay? So then what we have to do is combine these two things, meaning that we start with our images. We first quantumly project these images into the good space, which is the slow feature space. Notice that these quantum procedures many times have this problem that the outcome that you get is not the classical description, as I said, but the quantum state that corresponds to the description of the classical object that you're looking for. But for us, this is good enough, because what we need for the classification is just these quantum states. We don't need to translate the quantum states into classical data and then do the classification. It's OK for us to have the answer of the slow feature analysis as a quantum state, and then this is exactly what we use to do the classification afterwards. Okay? What we get is something like 98.5% accuracy, which is kind of comparable with, actually, it's exactly the same as the classical slow feature analysis technique that on the same data set. But this is, again, not exactly the best thing that one can do. Why? Because we are using techniques that have to do with dimensionality reduction. There are better techniques that people use nowadays which have to do with neural networks. So then we had to start looking at neural networks. OK, before that, we also had to look at what is the running time of this quantum algorithm. So as you can see, the classical running time is something like 10 to the 13, and we actually run the simulations on some HPC machine. And then I just put this slide on to see that the quantum running time depends very nicely on this number of images and dimensions. They're only in a log, but it has another 6 parameters in front of it. Okay? So one way to look at this is to say, OK, I ignore everything else and I have an exponentially faster algorithm, but this is not what we want to do here. We want to really understand if this algorithm has any chance of working in practice. So we calculated all these parameters for the specific data that arises from the MNIST data set, and we found some sort of ratio of 10 to the 7. Again, this does not mean that if I run this algorithm tomorrow or when I have a full-scale computer, you will get 1 million times better, but at least it gives you a gap that hopefully some of it will remain when you're trying to implement these algorithms in practice in the future. OK, so as I said, for me, the more interesting thing about these algorithms is not that you can do faster than the classical classification. It's more that the dependence of the running time of the quantum algorithm on the dimension and on the number of points is much more favorable, which means that you can keep much more information in your model, you can keep more dimensions, you can keep more features, and have a quantum algorithm that will spend, let's say, the same time as the classical one, but hopefully will give you much better accuracy results because it will keep more information about your initial points. Okay. As I said before, we wanted to say what can we do with neural networks, because neural networks is one of the most interesting techniques to actually classify. And again, it's the same kind of concept. You have a neural network. You start with some random assignment of weights. Then you have your training set, which is these images that you know that this is a 3, this is a 5, this is a 7. You feed these images into your neural network, and you try to update your neural network. You try to train it so that at the end, when it is trained, when a new image comes, the neural network by itself will tell you this is a 3 or this is a 7. Okay? So we started looking at feed-forward networks, which was kind of the more simple networks that we could see. And we used similar type of tools. We used distance estimation. We used quantum linear algebra. And we also had to find some clever way of storing these weights of the neural network during the training. And what we came up with is an algorithm, is a quantum algorithm for training classical neural networks that actually scales as the number of neurons and not as the number of edges, which is the running time of the classical feed-forward and backpropagation algorithms. Again, this is not the end of the story, in the sense that our algorithm also depends on many other parameters. So we gain by going from the number of edges, which for a fully connected graph is like n squared, we go to n. So we get a quadratic advantage when it comes to the size of the network. But also there are many other parameters which are there. And we basically have to see where is exactly the sweet spot where this type of algorithms can actually train neural networks faster than classical ones. The other thing we wanted to do, and this is also very important, is to look at the accuracy. Like, can we say something about how good these neural networks can be? And what we proved is that basically the behavior of the quantumly trained neural network will be the same as a robust version of classical feed-forward neural networks that we also simulated on real data sets like the MNIST classification, and we got exactly the same type of accuracy as the classical neural networks. So we have at least the same accuracy, and in many cases we can be faster. Again, if instead of being faster, you can increase the size of your neural network, you could expect to have better performance with the same running time. All right. So the last point I want to make is now, again, about classification. We want to go to the unsupervised case. So this is more difficult now, because no one comes and tells you, here are some images, and I tell you what are the labels. Here you just have points. You just have your data set. And what you want to do is you want to cluster similar things together. Okay? So if you can see simply in the picture, what you want is you want to assign for these sets of points in different color, a different label. Okay? So the main algorithm that one uses for this case is called the k-means. The k-means is the following. I start with the centers, random centers for these clusters, and then I assign the points to the clusters. Then I recompute the centers. I reassign the points. I do it a few times. After some point, my k-means algorithm converges, and then I output the centers of these clusters, and then I can easily label every point by just looking at which cluster is closer to the point. Okay? So this is the canonical way of doing unsupervised clustering. The good point about k-means, well, first of all, it's trying to solve an NP-hard problem, so it doesn't work all the time, obviously. In practice, it converges quite fast. But it also depends linearly on the number of points that you have and the dimension of the points, which makes it a very slow algorithm when you have many, many points or many, many dimensions. Of course, there are better algorithms, heuristic algorithms on top of the k-means that can make your algorithm run faster. Okay? So what we wanted to do is come up with a quantum k-means algorithm, okay, that basically will do the similar type of process. We start with some random clusters. And now, instead of estimating the distance of every point to the centroid, I just do it in superposition. And then I use some quantum linear algebra to come up with a new updated centroids as quantum states. And then we would also have to do some sort of tomography procedure to actually recover the classical description and go back and do the iterations. So I'm almost out of time, so this is my last thing. So the running time of the quantum algorithm depends on the number of clusters, the same as the classical. It depends on the dimension, the same as the classical. But we only depend logarithmically on the number of points, which means that if you have a case where your number of points are really the bottleneck of your algorithm, you can have millions and millions of points, then this quantum algorithm can actually run much faster than the classical one. Okay? And for the accuracy, what we proved is that the convergence is the same as you expect from a classical k-means, a robust version of a classical k-means algorithm. It means that we don't lose anything in accuracy compared to the classical algorithm, meaning that whenever the classical algorithm would work, the quantum algorithm would work, and actually it will be much faster. OK, so if I have 30 seconds, I just want to finish with this slide. I try to show you a few applications that we think that quantum computers might be helpful in the future. These algorithms are not algorithms that can be implemented in near-term machines. So I still think that machine learning and optimization is one of the main reasons why we should really try to build quantum computers. There are no off-the-shelf quantum solutions. It's not easy to find quantum algorithms. It's not just that we're missing the hardware. We have a lot of work to do on quantum algorithms and connecting quantum algorithms to real-world use cases. There's a lot of work to be done there. And I just want to say that the next steps would be that we want to build quantum computers. We want to build these random access memories. We need to find more applications. And my last comment is that I think it's very important to try and find algorithms that run in near-term machines. But I want to be able to continue to think big. I want to be able to continue to think of what can we do with real quantum computers, and really how can we harness the full power of quantum technologies and the full power of nature. Thank you. So there's one question there, and then someone will bring you the microphone.
Hi. Did you think of testing this on a more difficult data set than MNIST? Because
yes.
MNIST has the problem that it's a balanced data set. You have just as many zeros as ones, as twos, as threes, and then all the digits are quite distinct from each other, so it's not a very good test of anything.
It's usually the first test that someone does, in the sense that if it doesn't work there, then you don't expect it to work anywhere else. For the k-means, we also tried a few more data sets, like Iris and some more. The problem is that the only way we can test the quantum algorithm is by simulating the classical equivalent in some sense, and this will give you an exponential blow up in the time, which means that we cannot test very big things. We did test it on synthetic data, we tested it on MNIST, we tested it on Iris, and we'll keep doing a lot of other simulations. Yeah.
Hi, I was just wondering, in many machine learning problems, like the data is very large, getting the data in, how do you solve that problem?
Yes, so very good question. So here, what I'm talking about, OK, so the data is the data. So the process of collecting the data or putting the data in the data structures will be similar in the classical and the quantum case. For example, for the recommendation systems, whenever a user comes into the system and whenever they take a survey or they buy something, you need to take this data point and store it into the data, right? In many applications, what's really important is not the time that you spend collecting the data, which on Amazon, for example, is a continuous process. Is the time that when the user comes into the system, how fast can you actually recommend something? So the quantum algorithms are not going to give you an advantage on how you will, the time that you will take to actually store the data. What we want from a quantum algorithm is to at least not spend more time storing the data than a classical algorithm will do. So for example, here what we use some data structures where the time to store the new data is the same as it would be to just write down in an array, okay? But what we need is this ability to ask queries in superposition. So most of the algorithms that I showed you, I wrote it as having quantum access to the data, meaning that it's similar to the Grover algorithm, that I should be able to ask, to address my memory in superposition. There was a question here, sorry.
That was a great talk. I'm going to ask some real beginner questions, though, if you don't mind. So I'm trying to understand the dimensionality issue. So you're mapping this on the qubits, and you're getting, I guess, 3 dimensions per qubit, but I don't understand how the reals come in and get mapped to qubits, number 1. Number 2, since you have to evaluate it in some basis, I don't understand how those dimensions are retained. Mm-hmm. So the whole way that you're mapping the real world into this qubit world and retaining that information is a little fuzzy. So
I guess the main idea is that if you have a system of n quantum bits, you have 2 to the n amplitudes where you can store information there. So what we can do is that we can take a vector in 2 to the n dimensions, and by using only n quantum bits, we can encode the amplitudes of this classical vector into the amplitudes of this quantum state. This doesn't mean that I can take all 2 to the n amplitudes out of this quantum state. This is why it is not the same thing to have a classical description of a vector and have a quantum state that kind of encodes this vector. The question is, are there problems where this quantum state is useful for you and you don't have to actually figure out all the classical description? For example, the recommendation systems is one case, because what you need at the end is just sample one good product for a user. You don't need to figure out all the preferences of the user for all the products. You just need to be able to sample something with a good value. So this is how, in many of these cases, we can get away from the problem of having the solution as a quantum state and not as a classical description. And sometimes you have to pay, you do tomography, and you have a classical description at the end. But this you have to pay.